let's start. Let me introduce our guest today. We were very happy that Peter Boorman will give a talk today. Now, Peter is at the Astronomical Institute the Astronomical Institute of the Czech Academy of Sciences in Prague. And Peter has been a postdoctoral researcher. He's a postdoctoral researcher there right now, sorry. And he got his PhD in Southampton at Southampton University, where he did his PhD work on obscured accretion and growth of supermassive black holes. And his research interests in general include black holes, Monte Carlo radiative transfer modeling, big data analysis, and machine learning. And today he will tell us about his recent work on shining light on the census of supermassive black hole accretion. And yeah, we're very happy to have you. Okay, the stage is yours. Thank you so much, Peter. Please, we're looking forward to your talk.
Thank you very much. Let me just share my screen. I think that's the wrong desktop. One sec. Hopefully you can see my screen.
Yeah.
Perfect. Is this the right view as well?
Yes, yes.
Yes.
Yeah, perfect.
That's
Thanks.
good.
Okay. So yeah, thank you for the kind introduction, and thank you very much for the invitation. It's great to be here today to be able to talk about my work. Essentially, what is quite a large project, quite a large chunk of my academic career so far, all about obscured accretion, but also more broadly about the census of supermassive black hole activity. And I will explain a bit more about these different terms as I go on, but I would just like to say from the start that, I don't know what the setting is normally in things, but if it's okay, I would welcome if anyone has any questions during the talk, please just interrupt. I may not see if you raise your hand, so just interrupt and ask any questions that might come up. Okay, so, where's my cursor? Okay, can you see my cursor, by the way? Yeah, okay, great. Okay, so yeah, a very brief outline. So I was told that there may not be many AGN researchers in the audience, so I was just going to overview exactly what we mean by an AGN, what we mean by supermassive black holes in general, and why obscuration is important, as well as what actually I mean by this obscuration. Okay. Then I'll move on to how we search for supermassive black holes that are growing, and how we can use different wavelengths to be able to detect certain systems. And then I will then go on to discuss this idea of a census of supermassive black hole activity. And I will explain, in my opinion at least, what needs to be done and what's useful for constructing such a census. Okay. So in terms of AGN, so active galactic nuclei, so essentially what are they, right? So here I have two pictures of two morphologically similar galaxies. Okay, they're both face-on spiral galaxies, right? But if I was to ask you if you could point out which galaxy has the AGN at the center, hopefully you would say the one on the left, okay, because there's some sort of very bright point source of emission that's unresolved. That's the reason we're seeing these diffraction spikes, even though I think this observation was taken by HST, so a very powerful telescope. But it means that there's an extremely powerful source that's unresolved at the center, right? So there's an extremely powerful source of energy. Just to note, actually, that by the end of this talk, hopefully I would have convinced you that this seeing something in the optical does not necessarily mean that it's definitely an AGN, or definitely mean that it is not an AGN. And hopefully I'll convince you that this galaxy as well also harbors a very powerful AGN. So in terms of what's going on to produce such a powerful source of emission, it's now quite widely believed and confirmed in certain ways that it's the gravitational potential energy release from material falling onto a supermassive black hole. Here I'm showing an artist's impression, right, where you see a radio jet here being emitted from the center. You see the accretion disk, and the hottest regions are closest to the supermassive black hole. And then surrounding it, or that seems to be feeding the accretion disk, is these walls of obscuration, which is quite important for this talk. Okay. So starting off, the original studies were done in the optical, in astronomy, and also specifically for AGN. And more specifically, if you have a look at optical spectra of supermassive black holes, okay, they very, very broadly in the original studies were classed into two main regions, or two main classifications. Okay, so here in this schematic, I'm showing essentially one system, so an accreting supermassive black hole with approximate size scales. So you can see the supermassive black hole, the accretion disk, the broad line region, which is hot clouds that leaves it orbit around the very close regions to the supermassive black hole and accretion disk. And then further out, you see this red region, which is some sort of anisotropic axis symmetric obscura that's located on sort of 1 to 100 parsecs, very roughly. 100 is probably a bit large on these scales. And then, and mainly in the optical at least, composed of dust. Okay, and then in the green region here, I'm showing quite diffuse, partially ionized gas that's very prone to emitting forbidden lines in the optical. So things like the O3 line is a very famous line tracing this narrow line region. And the idea is that this gas is being excited by the accretion disk photons of the supermassive black hole. Now, on the left here, I'm showing an unobscured view. I'm being a bit misleading because I haven't included the torus, right? But the idea from the original, what was called the unified model, is that all of these different spectra, ones that where you can see the broad line region and where your permitted lines, so H alpha, H beta, other lines, are typically broadened by the rotation of this broad line region. But this idea was unified with the sources where you see very strong forbidden lines, okay, very narrow lines as well. So the permitted lines are also narrow. The idea being that you can't see down to this broad line region, okay? And so the idea was that if it could purely be placed on inclination, right? This was the original idea, called inclination-based unification. And if you imagine, for instance, if you were viewing this system in this direction, so through the red obscuration, you would see the narrow line region, you would see the strong forbidden lines, but you wouldn't necessarily see the broad lines from the broad line region, and then vice versa. If you were to view Polon, you would see the broad lines from the broad line region. This slide is quite a simplified case, right? Because you have other components, there are other things going on, but this sort of covers exactly what the unified model actually is. Okay. Okay, so, well, this is an X-ray talk. So what about X-rays, right? So it turns out that extrasolar, so X-rays from outside the solar system, are actually relatively young, okay? So the first observation of a source in X-rays outside the solar system was in 1962, which was awarded the Nobel Prize in, I believe, 2002, maybe. I can't quite remember the year. But this plot I've just basically reproduced from that original paper. Okay, so the experiment was on a rocket with some Geiger counters, effectively on board, was launched into space and would continually rotate and detect X-rays in random directions. Okay, and what they found, well, they were originally trying to look for solar X-rays being scattered off the moon, and they did find that. That's this small bump you see here. But what they actually found was a much broader, much brighter source, which was later discovered to be SCO-X1, one of the brightest X-ray sources on the sky. But for the purposes of this talk, the other thing they found, which was what was awarded in part the Nobel Prize, as well as SCO-X1, was this residual level of counts that was seen in every direction. right? So no matter what direction they looked at, they were always seeing an X-ray source, okay? And now, as time went on and different X-ray missions were able to study this, what's called the background in more detail. Here I'm showing an SED, right? So a spectrum where you have energy or wavelength on the x-axis and then the intensity on the y-axis. And essentially, if you were to look with an X-ray telescope of sufficient sensitivity in the corresponding energy band at any position on the sky and removed the sources that you could resolve, this is the spectrum that you would see. Okay, and it took a long time to try and figure out what was contributing to this very broad spectrum with a very broad, what's called a very broad hump, right, at around 30 keV. And it was a matter of open debate for quite some time. Okay. So bringing it back to AGN. So what about AGN X-ray emission? Okay, so here's another schematic of a little cartoon of a supermassive black hole that's accreting from the accretion disk. There's no obscuration yet, but there is a hot gas of electrons located very, very close to the accreting supermassive black hole. Okay, now this is dubbed the corona. I've shown it as a very small source above the supermassive black hole. This is just a random choice, right? No one really knows what the geometry of the corona is yet. But essentially, that hot gas of electrons is responsible for Compton upscattering the photons from the accretion disk, typically in the optical and UV bands, up into the X-ray regime. And that's where you see the primary emission, the primary X-ray emission from AGN. And that's also why it's an opportunity to study the closest regions to the supermassive black hole, because they're emitted so close to the source. Keep doing that. So this was quite a simplistic picture, of course, because it's quite rare that all of the X-rays being emitted don't interact with anything until they reach our telescopes, right? They'll, the chances are that they'll interact with an atom of some sort. And for the purposes of this talk, here's quite a grossly oversimplified way of considering what happens to that X-ray photon as it interacts with matter. Okay. So you have an X-ray being emitted from the AGN, it comes into contact with an atom, and we can consider one of three things happening, right? There's some finite probability that it will just be transmitted straight through the atom and it won't be affected in any way. There's a chance that it'll be absorbed, right? So an electron will gain energy in an atom, completely absorb the photon, and then can either emit a fluorescence photon, which is a photon with a very specific energy, which often gives spectral lines in the X-ray spectrum, or it can be Compton scattered by a stationary electron, which is predicted to be roughly stationary. Okay, and so this fluorescence plus Compton scattering spectrum, I'm going to refer to as reflection or reprocessed emission throughout this talk. And then the sort of unscathed X-ray photons, I'm going to talk as the transmitted component. Okay. So the first obvious option that we can have for reflection is that X-ray photons are reprocessed and reflected off the accretion disk. Okay, so this gives you a reprocessed spectrum, and depending on how close this reprocessing happens to the central supermassive black hole, you see some general relativistic effects. Okay, I won't talk too much about those in this talk, but this spectrum here that I'm showing is essentially colored by the spin of the supermassive black hole, assuming that the reflection is happening close enough that the spin can have a significant effect. And as you can see, that as you increase in spin, you get an emission feature here, which is the most common emission feature seen in AGN, the I and K alpha line, but you can see that it becomes broadened, right? So there's this tail, it's got this sort of blurred reflection shape, right? But then what's also important for this is that you can see there is a Compton hump, right? So this is the effect of Compton scattering, that you get photons given energy up to around this level of 30 keV, and also there's a finite temperature, and so there's this hump shape that gets generated. And you can see that it's a very broad spectrum with a hump at around 30 keV, which might sound a bit familiar from a few slides ago. Right? So this talk is more about obscuration, but just because the obscuration is further from the supermassive black hole doesn't mean that we don't get reflection. Okay, so this plot I'm showing in the inset is essentially assuming a specific model for the geometry of obscuration that's surrounding the AGN. This particular geometry is called UX clumpy. So it assumes a clumpy, just a random distribution of blobs in a particular torus geometry. And you can see that as you increase in line of sight column density up to this value of roughly 26, with the most dense material, you start to see this reflection spectrum, which again has a Compton hump at around 30 keV, but also very narrow fluorescence features, right? Because these aren't being broadened because there aren't general relativistic effects happening nearly as much level, just because the torus, or whatever this obscura is located on much larger size scales away. So just so there's a rough picture in your mind, just for reference. Just thought I'd talk a little bit about what exactly we mean by column density. Okay, so here I'm showing that as you increase with column density, it's actually akin to trying to view the sun through different levels of clouds in our atmosphere. Okay, so for instance, if you have a column density of around 10 to the 20 per centimeter squared, it's roughly akin to just viewing the sun on a cloudless day, right? But then as you get to these levels of 24 and 26, it's like trying to view the sun either through thick fog or trying to view through a thundercloud. Okay. And just going back to what I was saying earlier about intrinsic emission and reprocessed emission, you can see in this inset how the different components dominate as this column density increases. Okay. You can see that the transmitted component, you get this photoelectric absorption until it drops, and at this sort of level of being Compton thick, the reprocessed spectrum starts to dominate. Okay. So in a bit more general, just in case I start saying these phrases, there are three main categories for this column density that I'm going to be considering. The first is Compton thin, so that's when the column density is anywhere from 22 to up to 24. It essentially means that the Compton scattered spectrum, so this reprocessed spectrum, is significant, but it's not dominating or close to dominating the spectrum. Okay. Then there's Compton thick, which more strictly is 24.17, but there isn't actually a strict limit because it depends on things like abundances and things like that. But roughly 24, let's say. And it's when the reprocessed spectrum starts to be comparable around 10 keV, right, to the transmitted spectrum. And then you have reflection dominated, right, where the thing's so obscured that all you're really seeing is reprocessing over a wide bandpass. This is quite an extreme case where you even get reprocessed emission up to 100 keV, but essentially the reprocessed spectrum is dominating at around 10 keV. Okay. So hopefully you've noticed the similarity in the shapes. Okay, so you have a broad Compton hump-esque thing in the observed cosmic X-ray background, and the cosmic X-ray background is now known to be composed of the integral of diffuse, or the summed up emission of discrete point sources of emission. Okay, and so these are the spectra of AGN at roughly redshift 1 for these different parameters that I've colored them by. And so hopefully this can show you that some sort of reprocessing is important in the AGN population, seeing as though the CXB is actually composed of every AGN over cosmic time, and this is one AGN with a particular column density and one with a particular spin, right? And actually the latest model that's taken essentially taken all observed inputs and predicted the what's called the column density distribution for AGN, has found or suggested that 50 plus or minus 9% of all AGN out to approximately 450 megaparsecs should be Compton thick. Okay, so heavily obscured. And yeah, I'll be talking a little bit more about that as we go on. Okay, so hopefully I've explained did a bit of a crash tour of what AGN are and why obscuration is important. Now I will now go on to talk about how we can find growing supermassive black holes. So if we look within 5 megaparsecs, for instance, it just turns out that there are 3 AGN within 5 megaparsecs of the Milky Way, right? So this plot in the center is essentially supergalactic coordinates. So what this means is that every ring, the way I've plotted it here, is approximately 1 megaparsec. This clump of sources is the Milky Way and all associated satellites that are known, that were in NED. Then this clump is the Andromeda galaxy. And as you go out, these 3 sources here are Centaurus A, NGC 4945, and the Sicinnus galaxy. Okay, and it turns out that of these 3, all of them are at least Compton thin, so have NH greater than 23, and then 2 of them are actually Compton thick. Okay, so within 5 megaparsecs, it's not a sample, of course, but within 5 megaparsecs, 2/3 of the sources, right, are Compton thick. Okay, so you can begin to see that 2/3 is roughly consistent with this value of 50% found by Anama et al. With the CXP population synthesis. So you can ask, what if we go a little bit further? And one way to do that is hard X-ray flux limited selection. Okay, so what that means is, for instance, with the Swift BAT telescope, this is an all-sky monitoring telescope where you can detect sources in the hard X-ray band. So I'm showing it here, but it's 14 to 195 keV. Okay, so the idea is that at those hard energies, it should select obscured AGN efficiently because of the penetrating power of the X-ray photons. Okay, and that is true, right? This plot is showing the flux that you observe with the UX clumpy model, the same model I was describing earlier, at a particular column density divided by the flux you would see if it was completely unobscured. Okay, so as you can see, up to around 24.5, the hard X-rays are a very efficient selector of AGN, even into the Compton thick regime. So that's great. But above this level, so above roughly 24.5, 25 roughly, you can see that the fraction of sources is really decreasing, right? And that's for all covering factors of the assumed model geometry. It's a little bit blurry, I'm not sure why, but here I'm showing what the color is essentially showing in the color bar. So it's the thickness of the torus, right, in this particular model. And so essentially at the highest values, it's essentially if you were sat on the corona and looking out, you would see a sky that's completely covered. Okay. Okay. Now, this depletion of flux in the Compton thick band is seen in hard X-ray observations, right? This difficulty of selecting Compton thick AGN in the hard X-ray band. So here I'm showing the Compton thick fraction in the Swift BAT survey as a function of distance from the Milky Way, right? So as you can see, for the closest distance, you get quite large fractions, but then it really starts to decrease, right, in this sort of fashion with distance that really does tell you that it's likely some sort of selection effect against Compton thick AGN with distance. Okay. So this brings me around to the discussion of how can we select and find AGN. Okay, so we're interested in something called isotropic selection. Right, and I really like this quote from a paper by Guido Rizzoliti in 1999, where he essentially writes that the optimal sample should be limited in the intrinsic flux, i.e. before absorption of the active nucleus. Okay, so essentially, if you're going to select a sample and you want to understand how that sample grows in a particular way, right, it should be not selected based on or solely based on a property that is to do with absorption. Okay. So in the schematic, as I was saying, higher energies are more likely to be transmitted because they have higher penetrating power. But the reprocessed emission is also starting to dominate, but also the flux is suppressed above a certain column density, right? Which means that when you have a flux limit, when you have a flux threshold, it can be difficult to select the most obscured objects representatively of the remaining, often brighter, unobscured objects. Okay. Okay, and this is what sometimes called isotropic estimators. These are some cartoons I made, but essentially they're showing they're showing 4 possible isotropic estimators. There are some others that aren't really used yet in large scale, such as the submillimeter, which will probably prove to be very important as time goes on and more surveys are taken. But in the meantime, there's the radio emission, or more specifically, the low frequency emission coming from radio lobes, right? There's the infrared emission that's often coming from the dusty obscuration or the dusty material surrounding the supermassive black hole. There's the optical, where I've colored the narrow line region that I was describing earlier. So essentially diffuse gas that's emitting forbidden lines. And then there's the X-ray emission, where the corona at the center is the source of the emission. And it is affected by obscuration, like I was just saying. So if we go through each of these, okay, so just more of a recap, but we're just going to go through the pros and cons of each, okay, in terms of selecting sources irrespective of their obscuration. So first you have coronal X-ray emission. So as we were discussing just now, it's highly penetrating, okay? Especially in hard X-rays, it can efficiently select AGN up to 10 to the 24 and even 24.5 when it's really hard X-rays being detected. One very nice plot that I really like is from a review by Brandt and Alexander in 2015, where it essentially shows the benefit also with X-rays or hard X-rays in AGN is that you don't get nearly as much star formation contamination, right? So this image is NGC 3783 in the optical on the left. And as you can see, you see a lot of emission from the host galaxy. But then when you observe in X-rays, and I haven't written the band on here, but I believe it was hard X-rays in Chandra, so maybe 2 to 7, but I'll have to double check. You can really see that the emission from the AGN is a point source of emission coming from the center and not contaminated by the host galaxy star formation emission, which is a real benefit. Okay. Okay, so what about the optical? Right, so there's the optical narrow line region, as I was saying earlier. It's got a very large size scale, and so it means that it effectively bypasses the obscura. Okay, so what I mean by that is that you can view from any angle in this schematic, right, and you can still see some portion of the optical narrow line region flux. However, the O3 emission is also contaminated by star formation. There's large scatter in the line fluxes that have been found, and so it can be quite hard to estimate the intrinsic power of the AGN purely from the O3 emission, for instance, one of the most powerful lines detected from the narrow line region. Also, if there is a lot of large-scale host galaxy dust, it can redden these lines, and it means that when you compare the ionization levels with other lines to be able to determine if there's an AGN, it can give incorrect results because you can get this reddening of the lines. So then moving on to the low frequency radio continuum coming from lobes. So the unbeamed extended jets can serve as orientation independent just because they're typically associated with even larger size scales. Some have been found to be megaparsecs in length, right? So it doesn't really care so much about the orientation-based obscuration very close to the accreting supermassive black hole. What's more interesting is that recent surveys have found that radio jets may actually be more common in radiatively efficient accretion. So it means that potentially as survey sensitivities improve, we may be able to actually detect more and more AGN purely from the radio. But this does mean that currently the sensitivities aren't quite there to detect large samples of obscured and unobscured AGN representatively. And also there are some selection biases in the sense that this dichotomy that has been found to not necessarily be such a dichotomy between radio loud and radio quiet sources, but essentially finding that 10% of the population can be very bright in the radio relative to typically the optical. And no one really knows why that might be, if that's a real effect. And if it is, it would be another selection bias that should be accounted for, but it's widely sort of unknown at this stage. So then there's the mid to far infrared continuum emission. Okay, so this is a kind of it might be a little bit confusing at first, but the dust surrounding the AGN effectively acts as a bolometer. Okay, so it heats up and it emits radiation in the infrared, right? And that's great for obscuration, right? Because if you have an obscured line of sight, the dust itself is actually going to be emitting. Okay, so that's great. The reason I've shown this sort of hatched region on this schematic, this is polar dust, right? And this is just to show the latest results from imaging with some of the best ground-based telescopes that exist currently at the VLT. This is work by Daniel Asmus in 2019, and these are only just two sources of a large sample of sources that he was able to show the primary emission in these sources is brightest in the polar directions, which is the green line in these schematics. Just for reference, the green line is, I think, 200 parsecs or kiloparsecs from the paper. It's a fixed size scale, just to show how far away these sources are relative to each other. And this kind of indicates that the majority of the mid-infrared emission is not necessarily from the obscuration, even though the obscuration must still be there. And so that's why I included it on this schematic. What's important for this is that the anisotropy between a face-on and an edge-on system in the infrared is found to be around 1.4. So almost completely isotropic, right? Close to unity in terms of their flux levels. But as with the optical, star formation and host galaxy emission really can contaminate the infrared emission. Okay, and so it can really confuse an AGN signature if you only have the infrared available. Okay, so that was the main sort of background of my talk. And now I'm going to go on to some work that I've been leading myself to try and sort of consider different selection methods to try and construct some kind of AGN census currently and also in the future. So here I'm showing the selection that we decided to use for the NuSTAR local AGN NH distribution survey. It's quite a mouthful, but it's NuLANDS for short. And what's unique about this particular selection is that we used a selection detailed in Kiel et al. 1994, and also de Gruyp et al. In originally, I think, 1985, and then developed into 87. And essentially what we do is very simple. We take the IRAS point source catalog, the most up-to-date one, so version 2.1, and we throw out upper limits at 25 and 60 micron. So we only require detections at these two infrared wavelengths. Okay. Now we want this to be an AGN survey, so then we also follow the same method that was done previously. We throw out the zones of avoidance. So these are a particular latitude from the Milky Way disk that we see in the sky, and then also the Magellanic clouds are thrown away, which you can see here and here. They're taken out, right? Just so that we ensure that we're seeing, or more likely to see, galaxies or extragalactic sources. Okay, so now we have a sample of sources that are purely selected in the infrared. So the idea is that of these 4,253 sources, right, there's going to be a lot of non-AGN in there, but of the AGN in there, it should be representative of whether they're a type 1 or a type 2 AGN based on zeroth order unification. Okay, it should be isotropic. But now we want to actually measure the NH. And so how can we do that in AGN? So here I'm showing a slightly different survey selected that I'm working with called LASER, the local AGN survey. We selected a particular galaxy as hosting an AGN that had never been studied before. And so we proposed for NuSTAR data. But as you can see, the existing archival Chandra data is very well fit with just thermal emission from collisionally ionized plasma. Okay, and this is typically associated with host galaxy emission, right? So this is two components, but it's pretty well fit with just that component. But when you actually observe with NuSTAR, what you see is the reprocessing component, right, that I was describing earlier, how it turns into the ion line, but then also this Compton hump that you see, right? So this is really showing why NuSTAR is essential for studies of such sources, because it can be very difficult to disentangle the AGN from the host galaxy in these types of systems when you only have photons below, say, 8 or 10 keV. Just for reference, also, you can see this purple line. This is the transmitted component, just because it is showing how obscured this system is, right, under this particular model. And here on the right, I'm just listing some different samples, that some legacy samples that NuSTAR is currently or previously been observing sources from to try and exactly do this type of thing, to find obscured AGN that have been missed previously, but also to try and piece together some sort of census of AGN activity. Okay, so just some examples, in case you didn't believe me. Here are some examples of quite well-known and well-studied Compton thick AGN in the literature that have been either identified or studied by NuSTAR to be able to really piece together the different components that are responsible for the observed X-ray spectrum. So I'm not going to go through all of these, but you can really see in some of these plots that with the NuSTAR band, you can really start to piece together possible modeled components that are responsible for the observed spectrum. It really just wasn't possible previously. Okay, so after that little interlude, we have in NuLANDS, we have a sample of infrared selected extragalactic, or more or less, the majority should be extragalactic sources. But then we want to classify them. We want to find out which ones are AGN. Okay, so to do that, we use two methods. The first method was first detailed in Gehrels et al. In 1985. And essentially, we have 25 and 60 micron fluxes. And what we do is we work out the slope of the observed spectrum between those two fluxes. The idea being that if they peak towards slightly warmer temperatures, so slightly lower wavelengths, then it should contain a hotter component that's typical from, say, an AGN. Okay, and here I'm showing with a particular SED template model the range of spectra you expect when you normalize to 60 microns between a non-AGN and a pure AGN, and the selection is this shaded region that we're using. So this is the way that we're able to sort of classify these sources very roughly as a warm source that should be or should contain an AGN. The next method, as I was describing earlier, is optical spectra. Okay, so this is a very efficient way of classifying sources, but I did say earlier that it can miss some AGN due to large-scale host galaxy dust reddening, and I will circle back to this at the end of the talk, but just bear that in mind. But essentially, what was done is that we use broad lines to classify optically unobscured sources, and then we use narrow lines to classify obscured line of sight sources, okay, in the optical. Okay, so now we have a sample of what should be AGN, right? They're AGN in the optical, indicative of AGN in the infrared. And so now we want to test if we're actually being isotropic of the AGN types, okay, of type 1 or type 2. Okay. And so this schematic is showing the optical emission as traced by the O3 line, as I was describing earlier in the narrow line region, and then the far or mid to far infrared as traced by the 25 and 60 micron fluxes. And the thing is with these two, you can test if they're isotropic by taking the ratio of both of the fluxes, right? And seeing how they compare between the type 1 and the type 2 objects. So you take the flux ratio at 25 micron, and here's the sources, just at the individual sources. And then you can fit a parent population distribution to these data points, which I've done in the cumulative distribution you see above. And the blue and the red line show that they're basically equal, right? They're consistent with being entirely isotropic. And likewise, when you take the ratio, but with 60 microns, you see that they're extremely close. There may be a slight deviation, but it's not really statistically significant. So it's really strongly indicating that our sample is sort of isotropic of these two flux, two fluxes that are coming from distinctly different regions around the AGN. So we had a NuSTAR legacy program for these sources. As you can see in this plot, it shows that NuLANDS is very, very capable of selecting very diverse spectral shapes in the X-rays. Okay, so just for reference, the different colors are just showing the signal to noise, but I've colored them by their optical type. Okay, so 1.9s, they can be a little bit strange because they can show X-ray obscuration ranging from unobscured to Compton thick. Okay, CFOT2s, so these are typically obscured systems in the optical and often seen to be obscured in the X-rays as well. And then unobscured, so type 1s, and then narrow-line CFOTs are sources that are typically often unobscured, but also can have very soft X-ray spectra. And I've also ordered these roughly by their signal to noise. Okay, so you can see that as you increase in signal to noise going vertically upwards, the majority of the lowest signal to noise systems are not only CFOT2s, so obscured, they're also showing features that look like typical reflection spectra from distant obscuration, right? You have narrow lines and you have Compton humps in quite a large number of these, which sort of backs up this idea that we were talking about earlier, where obscuration really can affect the X-ray flux and the observed X-ray spectrum that you have. So this includes all of the sources in the sample. So this is 122 sources. I've also circled or drawn a box around the sources that were detected in the Swift batch 70-month catalog, so in ultra-hard X-rays. And as you can see, some of the brightest sources are the ones being detected in that particular selection. So then we have, this plot is exactly the same as previously, but I'm only plotting the NuLANDS sources. So the sources that have been observed their X-ray spectra that we get. So as you can see, and I've binned these by a particular signal to noise, that's why it looks like there's two bins, right? But some of these are extremely faint, as you would expect. But some of them are relatively speaking, very bright, with typical spectra, as I was saying earlier, with a narrow line and also a Compton hump. Okay. So what can we do with these, right? So here I'm showing all of the different AGN types that we can hope to model, and also the torus that we want to model as well. These are all the geometries of the obscura that I consider in our work. And the geometries range from semi-infinite slabs, so more of an analytical approach, all the way to spherical obscuras with polar cutouts, more exotic flavors such as warped disks that can cause the obscuration as it passes in front of your line of sight, for instance. Then you have clumpy models where you have clumpy distributions of gas, and also donuts, so toroidal distributions of matter, where you can decouple different components to assume different geometrical assumptions. So what do these actually look like in terms of spectral fitting? Here I'm just showing each of these model setups. So there's 23 in total, where the purple plots, it's a little bit hard to see, but the purple outlines are the ones of physically motivated torus models. So ones where you use radiative transfer, where you fire X-ray photons through a geometry of gas, and you bin up the X-ray photons that are detected as they pass through that gas, and you can get a spectrum. Then in the blue are and the orange are the phenomenological models based more on this slab geometry. And then I've also included some what we call basic models where we don't actually consider reflection components at all, right? So how do we fit these X-ray spectra when we have such varying signal to noise? We use BXA, so Bayesian X-ray analysis, which is based on nested sampling. So I can talk to quite a long time about this, so I won't go over it in too much detail. But essentially what this video is showing are a series of Compton thick X-ray spectra that I simulate at increasingly further distances to make its flux or its observed flux lower, and so its signal to noise lower. Okay, and as you can see, as the source drops below the background, when with typical fitting methods, you wouldn't be able to fit if you were just dominated by the background. This method of fitting essentially gives you a confidence region rather than a confidence point in your parameter space. So as you can see, as you get to even less than 0 source counts, so purely dominated by background, if you're fitting the background simultaneously, you know that the source can't be unobscured and above a certain flux level, because otherwise you would have detected it. Right? So that's why this region of the plot here stays unpopulated by the posterior points in these fittings. And one other key thing is that with this method of nested sampling, you get the Bayesian evidence, and the ratio of the Bayesian evidence for one model divided by the other can stand as a model comparison technique, right? So you can say that above a certain threshold for this factor, you can favor, say, model 1 over model 2, or vice versa. Okay. So that's great. We're fitting all of these different geometries, right? But there are some complications, okay? By fitting all of these geometries, you get what I've dubbed as geometric degeneracies, right? And so this is just one example of one source. So this is NGC 7674. And based on the base factor, we're selecting models. And from the fits, we select these two model fits, okay? So by eye, the model fits look very similar. There are different reprocessed components and different strengths of the reprocessed components. That's purely just because they're different models, okay, and different geometries. One is clumpy and one is a smooth toroidal distribution. But as you can see in the bottom panels, this is showing the posterior on column density that we get from the two models, and they're both selected. One is Compton thick, so above 10 to the 24, and one is Compton thin, so between 23 and 23.5, right? So these are quite drastically different findings. So how can we deal with that? Right? So one way that I came up with to deal with that is essentially to try and include every model that's selected in the ultimate fitting process, right? So this is quite a busy plot, but it's essentially showing the most favored model per source for all of the sources in NuLANDS, okay? And now if you actually consider all of the models that are statistically possible based on the Bayesian evidence, you can see that for all of these lines, some of them have a fainter line in the background, and that's all of the other models that are also possible, okay? For the source that I just showed, you can see it here. There's a very faint posterior at around 23, but then the most favored one is this Compton thick solution, okay? Now, we also include sources with no X-rays, and the way we do that is we essentially work out, so all of the sources with no X-rays are Seaford-2s, so we work out what the average column density is for all of the Seaford-2s with some hierarchical modeling, which I'll describe in the next slide, and then we work out essentially for the sources with no X-rays, we assign that as a prior, that posterior on NH as a prior to the final NH distribution. Okay, so this, in terms of the column density distribution, this is the main goal of NuLANDS. And essentially what we do is we take the observed X-ray spectra, as I've been saying, we then fit with a model to get a particular posterior on column density. And then based on all of those posteriors, we then fit for a global distribution in a hierarchical model. The reason it's called hierarchy is because it's hierarchical in this sense that you're starting from where you have the global population distribution that you're fitting, where just each of the individual bins are a free parameter in the model. Okay. And then, as you can see in this plot on the right, I'm shading by the 90% confidence region, and we have the various bins in column density. But the interesting thing is that we're finding that the Compton thick fraction, yes, there's a bit of uncertainty here, but it is starting to be consistent with this value of Anana et al., who found 50% plus or minus 9%. Okay, we're finding around 35, right, plus or minus 9. Okay. So one question based on earlier might be, how does this vary with distance? So here I'm just showing the same plot. The plot I just showed is the dashed gray line, okay? And then I'm doing the same hierarchical fitting, but as a function of distance from us. And as you can see, for all of these, the uncertainties that we get are consistent with the model. It's kind of indicating that we're selecting Compton thick AGN out to the distance of around 200 megaparsecs, representatively of the rest of the column density distribution. Okay. Now, the very last thing I just wanted to mention before I finish is just here. So I mentioned earlier that the optical may be missing some sources, right? So we're very interested in knowing that, because currently the Compton thick fraction is a little below this value from Anana et al. And so one open question is, how many of these systems are actually hiding an AGN that was thrown out because the optical classification couldn't pick them out as AGN? So here I'm showing some very preliminary work where I've done some simple sort of SED fitting based on the observed infrared to optical fluxes for some systems. And as you can see, in a number of these systems, there's quite a strong component of AGN heated dust that's needed, that's actually quite well constrained. Okay, so it may indicate that these systems may actually harbor AGN as well, that might need to be considered in the ultimate sample for a more complete sample. Now, I always quite like to end my talks talking a little bit about the future. I think the future is very X-ray bright, so to speak. Here I'm just showing one particular example. So with the power of Athena XIFU and also the proposed, currently under the proposal stage, high energy X-ray probe. Essentially, HEXP is kind of like a more extreme version of NuSTAR that goes from 2 keV up to 200 keV. And the XIFU will have a microcalorimeter, so an instrument that essentially has very, very extremely good spectral resolution. And I think this would be very important for many reasons, but if they can fly together, for instance, if they were to, it would be very useful for decoupling these different reflection scenarios that I introduced earlier at the start of my talk, right? So in the brown, you can see the distant reflection spectrum for this particular simulation. And in the blue, you can see the, or in purple is the actual relativistic reflection spectrum. And you can see that the data that you get with HEXP is suitable to be able to disentangle these components and to really start to study the obscura in tremendous detail in future AGN surveys. And these are obviously two of many missions. I've listed a few missions that you can get more information at the different web addresses down here. The soonest one to be launched is Accretion, which is also a microcalorimeter that will greatly improve some of these studies as well. So yeah, that's everything I was going to go over. Just in terms of some take-home points, hopefully I've convinced you that a supermassive black hole census really does require a multi-wavelength view, right? If you're really going to have a census of something, you really do have to understand your biases and be able to combine them in a complementary way. Now, based on that, NuLANDS is very complementary to hard X-ray selection. And based on this optical scenario that I've been describing just now, it provides a very sensitive lower limit in the most conservative case to the obscured fraction. And then finally, improved X-ray coverage, not only broadband, so with instruments like HEXP, but also spectral resolution from CRISM and Athena XIFU. It's going to be essential for not only understanding the column density along the line of sight, but also the geometry of the obscura as well. So on that, I will end. And if you have any questions, I'd be happy to take them.
Okay, thank you for this very interesting talk. Are there any questions? Okay. Okay, let's see. I see Tolga has a question.
Hi, Peter. Thank you very much. Really, very good talk. I wanted to have your opinion on like this Russian mission, Spectrum Röntgen Gamma. You know, they have this ART-XC telescope, which is surveying in the hard X-rays. I was wondering maybe if you may have an opinion on how much will it be effective in discovering newly obscured AGN. I mean, now that there's this conflict, I know that they turned the eROSITA off completely, but the ART-XC is still going on as much as I know. So do you may have any, you know, opinion on how that survey will have in all these things, especially about obscured AGN stuff?
Yeah, that's a fantastic question. Yeah. So in terms of obscured AGN, from what I understand, it still has, well, it's a survey instrument, right? So it's going to be able to really detect in potentially better, better flux levels than SwiftBat, for instance. But I think it is still slightly lower in terms of effective area than NuSTAR, if I remember correctly. But I think it has a larger field of view. So yeah, it's definitely potentially very, very useful for trying to discover new obscured AGN. The reason I didn't mention it for the specifically for the geometry is because for the geometry, it's really starting to arise that you really do need very high spectral resolution and also this very broad bandpass. But yes, definitely data from SRG in particular will be very useful in combination with current and future instruments as well.
Yeah, they definitely can't create such spectra. I mean, we've seen its data. It's basically fluxes and some detections like for localization, let's say. But I guess in time it will at least help in maybe using multi-wavelength data and so on, identifying some of these whatever X-ray sources as obscured. Okay, thanks.
Yeah, definitely. And if I could add as well, like in terms of in terms of the infrared, so all sky surveys in the infrared, such as from WISE, it can be very useful to cross-match detections in WISE and then non-detections in the X-ray as well. So even well-known galaxies that are non-detection in the X-ray, but selected as being AGN in the infrared, that can be extremely useful because you would expect the most obscured sources to not be detected in such hard X-rays as well. So yeah.
Thanks.
Okay, I see there's another question from Echel Kilaji.
Yes, can you hear me?
Yes.
Okay, I was wondering, so you are mostly limited by the distance limit of the X-ray telescopes, yes?
For a certain flux threshold, yeah.
Yes, but with this future telescope, I mean, can you push it to up to higher redshifts, maybe?
Yeah, that's a fantastic question. Yeah. So when I was describing the CXB, it is true that this shape of like a broad Compton hump does match obscured AGN and also just a reprocessing spectrum, but at redshift 1. Okay, and so a lot of surveys have also shown that at high redshift, this sort of obscured accretion should be more dominant, right? And so yeah, it really does offer the question of like how many of these things can we detect at higher redshift, right? And that's actually one of the main or one of the key survey science goals for Athena, the wide field imager. And I think I might actually have. Here's another compilation I made. So this plot in the center is a WFI spectrum of with 1 megasecond of a redshift 2.6 quasar that's Compton thick. And you can see that you can not only detect the Compton hump and the underlying continuum, you can start to do some really nice science with the ion line, for instance. So yeah, it's a great question. In terms of actually selecting them, yeah, I think that Athena and other instruments where the flux threshold is going lower and lower will be very important.
Can I ask one more question? if there's no one else. Okay, this is more like, for example, if we have a NuSTAR data of an AGN, what is the best recipe to test if it's Compton thick? I mean, you showed many models. Probably we need to read many papers to get the answer. But I mean, since you deal with this data, I mean, what would you suggest, for example?
Yeah, that's a great question. So, so if you're going in it blind when you don't know about the source in terms of other wavelengths, I would recommend checking in, say, the infrared or optical, just to understand a little bit about how bright it should be intrinsically in the X-ray, because there are correlations between, say, the infrared and the X-ray and the optical and the X-ray. That can give you some sort of basis, just because there is this confusion, right, between reflection spectrum from an unobscured AGN and an obscured AGN. Okay. Now, in terms of it being Compton thick, if you're sure that it's obscured, for instance, if its flux level is lower than the predicted intrinsic by some sort of significant amount, then yes, I would I would recommend, essentially, if you can time-wise afford to do it, try out as many different obscure geometries as you can, right? And that's essentially what I tried to do with NuLANDS. Because as I showed, you can have a Compton thin scenario that's Compton thick in another geometry. Okay, but essentially to look at those, and based on physical reasoning, right? So for instance, the predicted intrinsic luminosity should agree roughly you may consider it should agree in some scenarios with the predicted intrinsic flux from, say, the infrared. And so that might give you a way to throw out some particular models. You can also use the Bayesian evidence, like I was describing, but to have a really strict cut or a threshold of Bayesian evidence or any model comparison threshold to throw out models, you do tend to need to do some sort of null hypothesis significance testing, just where you sort of simulate a lot of data from your models to be able to say at what level of this model selection threshold can I actually throw out a particular model. Right. But yeah, I think to really understand the degeneracies between parameters and also degeneracies between geometries of individual models, I think it really does require using more models than, say, just one or two.
Thank you.
Thanks.
Okay, any other questions? Okay, if not, I have a quick question. So when you look at really distant sources, I mean, you said this, I mean, this mainly will kind of, you get extinction and this will lower the intensity. But will there at some be a point that it also affects the spectral properties so much that this might, say, be problematic with this classification?
So do you mean in terms of the K correction?
In general, you know, I guess the further the source is away, the more can happen on the way. And you're very interested in the region, what happens around the AGN and the obscuration there. But if a lot of things happen on the way, this might affect the spectral properties and what you see in the different bands. And so I just wonder if this might be a concern at some point, and if there's a limit on the distance that you can use there, actually.
That's actually, yeah, that's a very, very good question. I don't know if this plot maybe shows it, but essentially in X-ray column densities, previous studies have found that it can be quite difficult to achieve Compton thick columns from the host galaxy, right? So the host galaxy of the source. But below that, you cannot be sure, especially at higher redshift when it's harder to resolve out these components spectrally. It can be very difficult to determine which obscuration is coming from the host galaxy and which is coming from some sort of circumnuclear obscura. Okay, so in terms of understanding how this obscuration changed over redshift and things like that, it can be very difficult to tell you, if this obscuration is coming from, say, the host galaxy or the circumnuclear obscura itself. And so that can be linked to your interpretation of what you're essentially getting out of these studies. So yeah, it's a very good question.
Okay, thank you. So I see another question now by Seval. Please go ahead.
Hi, hello, can you hear me?
Yes.
Yeah.
Okay, thank you so much for your good speech. I'm so delighted to listen. I have a question, even though it is not directly related with your presentation topic. It might be basic, but just wondering, and I'm asking. A normal galaxy can transform an AGN after merging another galaxy, right?
Sorry, could you repeat that? Sorry.
A normal galaxy like Milky Way, it's a normal galaxy without an AGN in the core. Can he transform an AGN after merging a galaxy?
Oh, so can it turn into an AGN after merging?
Yes.
Yes, yeah, that's very true. So there are systems that are often very dusty, called LURGs and ULURGs, which are often associated with mergers. And the thing is that either the supermassive black holes have merged, but that's typically unobservable with current instrumentation, just because for that sort of resolution, you need very good spatial resolution. But they're typically, oh, sorry. Oh, but typically you need, yeah, very good resolution. But in terms of the infrared selection that I was discussing, you can also get very red systems, which are typically picked up as being AGN, even though they can be very obscured and not necessarily AGN, but it can be very difficult to determine if they do contain an AGN. So observationally, it can be quite tricky. Yeah.
Okay, can I think inversely? What about an AGN? It can be a normal galaxy in its lifetime.
Yes. Yeah, yeah.
Okay, how can we explain the mechanism behind this? What is happening in the active galactic nuclei that it is becoming a normal phase?
Yes, yeah, that's a very good question. So there's well, one type of system that's maybe quite relevant are called Voorwerks. So they're typically systems that are seen to be relatively normal galaxies, right? But they have a region of ionized gas somewhere around them. And the idea is that previously they're an AGN, and then for whatever reason they've turned off. And so the narrow line region is no longer being powered, right? So you end up with these giant clouds of ionized gas. So we do see them, but in terms of the reason that these things would, these supermassive black holes would stop accreting, I think it's an area very open to research at the moment. No one really knows exactly what could be shutting off these systems.
All right, I get it. One more thing. Do we have any observable evidence about that?
Of turning off AGN?
Yes, very indeed.
Yes, yeah. So these are these Voorwerk systems that I was talking about. So it's a bit of a weird spelling. I can never get it right. But there was a paper by, well, the most recent one that I know of has Keel as one of the authors, but then there's been previous work by Sartori et al. If you wanted to look them up. But essentially, yeah, they're galaxies where you see an ionized cloud of gas that's believed to be the old remnant of a narrow line region, because the AGN has switched off at some point.
Okay, thank you so much for your explanation.
Thanks.
Your microphone is off, Kai.
Okay, sorry. Yes, I realized. So if there are no further questions, then thank you so much for this very nice talk. And yeah, for answering all our many questions. And yeah, let's close the session here. Thanks so much. Have a good day and see you next time.
Thank you very much.
Thank you very much.
See you.
Okay. See you.